Hello everyone and welcome back to another calculus video. In this video we are going to talk about area and arc length of equations that are written in terms of polar coordinates. So the idea of this formula goes back to the area of a sector. So if you remember back to pre-cal trig, we talked about area of sectors. A sector is just a small piece of a circle, and that area equation was 1/2 theta r squared. So if we're integrating with respect to theta, we're thinking about small increments that we're changing that theta value. So we're adding small sectors up um, throughout an interval. And when we add an infinite number of small sectors up, or well, an infinite number of anything up, then it really becomes an integration problem. So that's where this formula is coming from, where r is equal to f of theta. So you can see this is 1/2 r squared theta, but we're thinking about theta being super small and splitting this into an infinite number of small pieces. So when we integrate, it's going to be 1/2 the integral from alpha to beta, where theta lives between alpha and beta, of f of theta quantity squared times d theta. So let's look at a few examples. So this first one, we want to find the area of one petal of a rose defined by the equation r equals 3 sine of 2 theta. So we need to figure out how we can trace one petal. So I'm going to pull this up in Desmos. We need to figure out what my theta bounds are going to be. So we're going to find bounds on theta. So when I graph 3 sine of 2 theta, we see that this is a rose and it's got 4 petals. We want to know the area for one petal. So let's see if we can figure out what bounds are going to be. To me, it looks like it's probably going from 0 to pi over 2. And that would give me that petal in that first quadrant. We could create that table of values and we would see how this is traced. We could also do this in the graphing calculator. So I'm going to put this mode in not parametric, polar. So I need this selection right here. Hit enter. So when I go to y equals, it's going to say r equals, and we're looking at 3 sine of 2 theta. The theta is the x value. And then if I go to, let's see what my window is set to, from 0 to 2 pi. So when I hit graph, you'll see all 4 petals. We want to know how to trace one, so we could play with this until we get just 1. Pi over 2. And then I'm going to go back to y equals, because this will actually show you orientation. If I change this line here, it will show me how it's traveling around that curve. So let's hit graph. Looks like it didn't save my setting. Let me try that again. And then let's click OK. And then now let's hit graph. So see my signs changed, and it's going to show this dot and how it's traced. That went super fast. I may have a difficult time doing this on the computer because it's a little bit more powerful than on the um, like a handheld calculator. Let's try that one. See if that does it. Yeah, it's just going so fast that it's having a hard time. You change it back so it does show me the lines. We'll try it one more time. Let's see if I can make my step size really small. Go to window. Wait, 001. You would not want to do this on your calculator because it will slow it down. But since I'm using my computer-based one, it's just moving too fast for us to see orientation. So if I hit graph, now you can see how it's moving along. So it's moving in that counterclockwise position. And going from 0 to pi over 2 is only going to trace that petal one time. We do not want to trace it more than one time if we're looking for area. So that's going to be from 0 to 2 pi. Just kidding, pi over 2 is what we said. Pi over 2. So then let's set up and integrate. So area is going to be 1/2 times the interval from 0 to pi over 2. And I'm looking at 3 sine of 2 theta. And that's what I'm squaring. Remember, it's based on that area of a sector. So that's that radius and how that radius is changing for all of those different sectors that we're adding up. So when I square that, I'm going to get non-sine squared of 2 theta, d theta. I'm going to pull that non out, and then I'm going to use a power reducing formula for the sine squared. So my power reducing formula says that the sine squared of u is equal to 1 minus cosine of 2u all over 2. So here my u is 2 theta. So I'm going to have 1 minus cosine of 2 times 2 theta, which is going to be a 4 theta all over 2 d theta. And I'm going to pull that 1/2 out. So now I have a 9 over 4, and I'm integrating from 0 to pi over 2, 1 minus cosine of 4 theta d theta. So when we integrate this, we got to think about splitting that integral into 2 pieces. We're going to integrate 1 d theta, which is pretty easy to do. And then we're going to subtract and integrate cosine of 4 theta d theta. So when I integrate 1, I'm just going to get theta. And then that second one's going to require a u substitution. So we're going to think about u being 4 theta. So the derivative of that is 4 d theta. So I need a 4. Now I'm going to compensate with a 1/4 out here. Let me see if I can clean that up just a little bit. Wow, I am having technical difficulties today. There we go. That's better. So when I integrate cosine of u, I'm going to get sine of u. So that's going to be sine of 4 theta, and we need to evaluate this from 0 to pi over 2. Oh, I forgot the 1/4 right there. So I'll put that sine over 4. So theta minus sine of 4 theta over 4. Bring this up here. So when I plug in pi over 2, I'm going to have pi over 2 minus 1/4 times the sine of pi over 2 times 4, which is 2 pi. Subtract, and then now we need to plug in the 0. So I'm going to have 0 minus 1/4 times sine of 0, and sine of 0 is just 0. So that whole parentheses set 0, and sine of 2 pi is also 0. So we're left with 9 over 4 times pi over 2, which is 9 pi over 8. So that's the area of one petal. So if I wanted the area of all of them, I would just multiply by 4. Four times 9 pi over 8, which would be 9 pi over 2. Example 2 is asking us to find the area outside of the cardioid r equals 2 plus 2 sine of theta, and inside the circle r equals 6 sine of theta. So we want the area between those two figures. So I'm going to graph this first so we can see what the picture looks like. So here's my cardioid in blue. Here is my circle in green, I want the area outside the cardioid, inside the circle, which would be this area between those two figures. So I'm going to have to figure out the bounds for this. So to find the bounds, I'm going to have to set these equations equal to each other. 2 plus 2 sine of theta is equal to 6 sine of theta. So let's move this over to get the sines on the same side. So now I have 2 equals 4 sine of theta. Divide by 2. I have 1/2 is equal to sine of the theta. So if we look at the unit circle, we want to know where is the y-coordinate equal to 1/2. That happens at pi over 6 and at 5 pi over 6. So those are my bounds for this figure. So if I want to know the area between, we can use some ideas that we talked about in Calc 1 where we're talking about the top curve minus the bottom curve. So for this one, it would be the circle minus the cardioid. So when we integrate, area is going to be 1/2. We're integrating from pi over 6 to 5 pi over 6, and it's going to be the circle, which is 6 sine of theta minus cardioid, which is 2 plus 2 sine of theta. And remember, we're thinking about the area of a sector, so we are squaring both of those R values. Hey everyone, so I paused the video so I could write out the solution. Now I'm going to come back and I'm going to explain what's happening in each step. So before we were looking at the area equals 1/2 times the integral of, it's going to be the circle squared minus the 1/2 the integral of the cardioid squared. So the circle is 6 sine of theta. The cardioid is 2 plus 2 sine of theta. So I'm going to put that together in one integral. So I have 1/2 times the integral of pi from pi over 6 to 5 pi over 6. So it's going to be 6 sine squared, which is 36 sine squared, minus the cardioid, which is 2 plus 2 sine theta squared, which is 4 plus 8 sine plus 4 sine squared. So when I distribute that negative here and combine like terms, I'm going to have 36 sine squared minus 4 sine squared, which is a 32 sine squared. And then I'm going to have a minus 8 sine and a minus 4. That's what I'm integrating. Now I could pull that 1/2 in so I don't have to keep it on the outside. And when I do, that's going to reduce those coefficients. So I'm going to have a 16 sine squared minus 4 sine minus 2. So I can integrate sine and then that -2 pretty easily, but I've got to use a power reducing formula for sine squared. Sine squared is equal to 1 minus cosine of 2 theta over 2. And we're going to reduce those coefficients. 16 divided by 2 is 8. So it's 8 times the parentheses set of 1 minus cosine of 2 theta. And then I have minus 4 sine minus 2, and I'm integrating with respect to theta. So I'm going to combine some like terms again. So I'm going to have 8 minus 2 gives me a 6. And then minus 8 cosine of 2 theta minus 4 sine of theta. Now when I integrate, like I said, I can integrate the number and I can integrate the sine piece easily, but that cosine of 2 theta is going to require a u substitution. So I'm going to split this up between two integrals. So I'm integrating 6 minus 4 sine of theta, and then I'm going to integrate the minus 8 times cosine of 2 theta separately. So when I integrate 6, I get 6 theta. When I integrate -4 sine of theta, I'm going to get a positive 4 cosine of theta. And then I've got to do a u substitution. My u for cosine of 2 theta is 2 theta. So du is 2 d theta. I needed 2, so I can multiply a 2 in if I compensate by a 1/2. So that I'm really multiplying by a well-chosen 1. So now I'm going to have a -4 on the outside. And when I integrate cosine of u, I'm going to get sine of u. So I've got 6 theta plus 4 cosine of theta minus 4 sine of 2 theta. And now I need to evaluate that from pi over 6 to 5 pi over 6. So I'm going to have to find the cosine of 5 pi over 6, and then I have to find the sine of 2 times 5 pi over 6. And then when I plug in the pi over 6, I'm going to need cosine of pi over 6 and sine of 2 times pi over 6, which is pi over 3. So we're going to keep that unit circle handy. So I have 6 times 5 pi over 6, which is 5 pi, plus 4 times cosine of 5 pi over 6, which is negative square root of 3 over 2, minus 4 times sine of 5 pi over 3, which is -4 times a negative square root of 3 over 2. And then we're going to subtract, and everything else is going to go in a bracket. We have to remember to distribute that negative. So I'm going to have 6 times pi over 6, which is going to give me a pi, plus 4 times cosine of pi over 6, which is 4 times square root of 3 over 2, and then a -4 times sine of pi over 3, which is -4 times square root of 3 over 2. So you can already see some things are going to cancel. In the end, we're going to be left with just that 5 pi minus pi, and that's going to give us 4 pi for that answer. The last problem we're going to do is going to be in terms of arc length. We're going to let f be a function whose derivative is continuous on the interval from alpha to beta, and the length of the graph from theta equals alpha to theta equals beta is equal to the integral from a to b is the square root of f of theta quantity squared plus f prime of theta quantity squared. So let's look at an example. Let's say we want to find the arc length of the cardioid r equals 2 plus 2 cosine theta. So I'm going to go to my Desmos, or you can do this in a calculator. So there's my cardioid. I need to be able to trace it once. So if we just plug in some bounds, I'm going to start with 0 to pi. You can see it only traces half of it. If I go 2 pi, it traces the entire thing. We could do the same thing in our graphing calculator. So this was 2 plus 2, 2 plus 2 cosine of theta. And I'm going to change my window to move a little bit faster. Let's use my theta step to be 0.01. And my theta max to be 2 pi. And I've got this set up so it will trace. And you can see how it's tracing the orientation it's going counterclockwise. And we could do the same thing just with parametrics. If we wanted to, we could put this in parametric mode. The TI calculator really is nice to be able to see that orientation. So we're going to have to find our derivative of this. So r prime is equal to, when I take the derivative of 2 plus 2 cosine of theta, derivative of cosine is negative sine, so it's just going to be -2 sine of theta. So when I plug everything in my formula, it's the square root of r squared plus r prime squared. So I'm going to have 2 plus 2 cosine of theta that I need to square, plus -2 sine that I need to square. So I'm going to get, when I square out 2 plus 2 cosine theta, I get 4 plus 8 cosine theta plus 4 cosine squared. And when I square -2 sine of theta, I'm going to get +4 sine squared. Now notice I've got a 4 cosine squared plus a 4 sine squared. If I factor that 4 out, I'm going to have 4 times cosine squared plus sine squared, and we know that cosine squared plus sine squared is equal to 1. So this is going to be 4 times 1, which is just going to be a 4. So then I've got 4 plus 4, which is going to give me an 8. So I have 8 plus 8 cosine of theta under that radical. And I'm going to tweak that a little bit. I could pull a 4 out. And so I have 4 times 2 plus 2 cosine of theta. And the reason I would do that is 4 is a perfect square. So if I take the square root of 4, I'm going to have a 2, and I'm going to pull that outside of the integral. So I have reduced this to 2 times the integral from 0 to 2 pi of the square root of 2 plus 2 cosine of theta. So we got to think about how are we going to integrate this. And we're going to use a little trick. We're going to tweak this using one of the identities that we learned back in trig. But it's going to take a little bit to manipulate that. So we need to tweak 2 plus 2 cosine of theta. Here's what we know. We know that cosine of 2 theta is equal to 2 cosine squared minus 1. Wouldn't it be nice if we could take this and write this as something squared? Because if I take the square root of something that's squared, then that square root and that squared is going to cancel for us. So let's see if we can tweak that. So cosine of 2 theta is equal to 2 cosine squared theta minus 1. Let's solve that for cosine squared. So I'm going to add 1 and then divide by 2. So I'm going to have cosine squared equals cosine of 2 theta plus 1 over 2. So that looks really close, right? Let's multiply both sides by 4. So if I do that and I reduce, I'm going to end up with 2 cosine of 2 theta plus 2 is equal to 4 cosine of theta. That's really close to my goal of 2 plus 2 cosine of theta. It's just I've got a double angle here. So let's do a u substitution. Let u be equal to 2 theta. So then theta, if I solve that, would be equal to u over 2. So now I have 2 cosine of u plus 2 is equal to 4 cosine squared of u over 2. So we derived something we could use. So that 2 plus 2 cosine of theta could be rewritten as 4 cosine squared of theta over 2. So that's what we've done in that next step. And now we're going to take the square root of something that's squared. We can think about that as a square root of 2 cosine of theta over 2 quantity squared. Okay, but when I take the square root of something that's squared, I really have to think about those absolute value. So if I were to graph that function, it's going to have positive and negative value. So I'm in Desmos, and I'm looking at r equals the square root of 4 cosine of theta over 2 quantity squared. So that's what that graph looks like. That looks like what we started with in that very first step. Let me pull that back up. If we were to graph this guy here, integral from 0 to 2 pi of the square root of f of theta squared plus f prime of theta squared, it would look identical. All of these steps are identical. It's producing the same graph. So why is the absolute value necessary? Well, let's pretend it's not. Let's don't graph it. Do I get the same picture? And you can see that I don't. It flips it. So it's not, this integral will not produce the same thing as this. But if I look at that absolute value, it does produce the same thing as that. But we have a problem, right? Because we can't really integrate absolute value. So what if we were just to go from 0 to pi? If I just integrate from 0 to pi, and then I double it because of the symmetry that we have here about that axis, then we'll be able to get the same answer. So that's what's going to happen. I'm going to rewrite that absolute value as an integral from 0 to pi, adjusting those bounds. And then I went ahead and pulled that 2 out. So then I have a 4 out here. So I'm integrating 4 times the integral from 0 to pi cosine of theta over 2. No absolute value there because we adjusted the bounds to account for the absolute value. But now I need to double that because that's only going to give me half of that answer. So I'm going to multiply it by 2, which is going to give me 8 here. So I'm going to have 8 times the integral from 0 to pi of cosine of theta over 2 d theta. So now we're going to do a u substitution. How do we integrate cosine of theta over 2? We're going to let u be theta over 2. So du is 1/2. We're going to compensate with 2, which is going to give me a 16 on the outside. And when I integrate cosine of u, I get sine of u. And then when I plug in my bounds from 0 to pi, I'm going to have 16 times sine of pi over 2 minus sine of 0. And sine of 0 is just 0. We know sine of pi over 2 is 1, so it's going to be 16 times 1, which is 16.